Let's start with the syllabus of alcohols, phenols, and ethers. We'll be learning about alcohols, the nomenclature, methods of preparation, physical and chemical properties of primary alcohols only, identification of primary, secondary, and tertiary alcohols, as well as mechanism of dehydration. Phenols, on the other hand, we'll be studying about nomenclature, the methods of preparation, physical and chemical properties, acidic nature of phenol, electrophilic substitution reaction, uses of phenol. And in ethers, we'll be studying about nomenclature, methods of preparation, physical as well as chemical properties and uses. In this video, we will be going over all of these topics and the mechanism part of this chapter will be in the next video. In this one, we'll just be discussing all of these concepts in detail. Let's start with the classification of alcohols. Alcohols, based on the number of OH groups, they're classified as monohydric, dihydric, and trihydric, as well as polyhydric. So if in case of monohydric, it depends based on the carbon the OH group is attached to. We are further classifying it as primary, secondary, and tertiary. So primary just has one other carbon atom attached. This one, secondary, has two, and tertiary has three. The next one is based on the compound containing a CsP3OH bond beside a CC double bond. So beside the CsP3OH bond, you have a CC double bond. So that's why you have allylic as well as benzylic alcohols. So in case of allylic, you have a double bond. In case of benzylic, you have an aromatic ring. The third is compounds containing CsP2OH bond. So the OH is actually attached to the carbon atom, which is bound to another carbon atom with a double bond. And that example is a vinylic alcohol, as it is given over here. Next, classification of phenols. Phenols are again based on the number of OH groups, are classified as monohydric, dihydric, and trihydric phenols. Ethers, on the other hand, are classified as simple or symmetrical ethers and mixed or unsymmetrical ethers. So in case of alcohols and phenols, you have OH as a functional group. In case of ethers, instead of a hydrogen in alcohols, we have another alkyl group, right? So if both the alkyl groups are same or similar rather, or the same one, it's called a simple or a symmetrical ether. Mixed or unsymmetrical ether, on the other hand, have very different groups. So here you have C2H5 and here you have a CH3. So these two are two different groups. So that makes this type of ether called as a mixed or unsymmetrical ether. Nomenclature. I believe this is very important for your exams. Like nomenclature is basically asked every single time. So first of all, you need to be thorough with respect to the nomenclature that you've learned in grade 11. If you are doubtful about that, I suggest just go through that once and then start with the nomenclature for these chapters. So for alcohols, generally the common name, that's the usual name, the name of the alkyl group and the word alcohol is added to it. So CH3OH is a methyl alcohol. C2H5OH would be ethyl alcohol. So common name, just the name of the alkyl group, beside that the word alcohol is added. Iopatning, on the other hand, you have the suffix OL. So the alkane, suppose methane, right? Methane, the E from methane is removed and the letters OL are added. Okay, so the position, obviously, we have to denote it, and the carbon chain is numbered such a way that the OH, the carbon attached to the OH, gets the smallest number. And all of these compounds they only contain like one functional group, that is the hydroxyl functional group. But if you have two or more functional groups in the compound, it will follow the order of priority. And you have learned that in grade 11. If you are doubtful about that, do check out the video that I have uploaded about the same. So in case of polyhydric alcohol, basically the ones which have more than one alcoholic group in this case. So di is indicated by the word, if there are two alcoholic groups, it's indicated by di. If there's three hydroxyl groups, they're indicated by tri, and all of that is before OL. So for example, here you have 1, 2. That is ethane. So ethane, 1, 2, diol. This is propane. This is a propane chain. And you have three alcoholic groups attached. or three hydroxyl groups attached. So propane 1, 2, 3, that is 1, 2, 3. All the three carbon atoms are attached to an alcoholic group or a hydroxyl group, and the name becomes propane 1, 2, 3 diol. No, triol. I'm sorry. So all of this, I mean, this is just the basic understanding. Here you have two groups. So methyl will come up as a prefix, and the alcohol will be the suffix because it's the principal functional group in this compound. Next, you have phenols. In phenols, first of all, 1, 2 disubstituted is going to be ortho, 1, 3 is meta, 1, 4 is para. So when you just have this benzene attached to an OH, that's called as phenol. Both IUPAC as well as common name is going to be phenol. Next, you have the benzene ring, the OH, and the CH3. So phenol gets position 1 and the CH3 gets position 2. So 2-methyl phenol, it's also called as cresol. So this is 3 and this is 4. This is based on the position of the CH3 group in relation to the position of a OH group. Next, dihydroxy derivatives. They are basically 1, 2 benzene diol. So when you have two hydroxyl groups, we are not going to call it 1 hydroxy 2 phenol. That's wrong. Instead, we refer to them as benzene diols. So benzene 1, 2 diol is first and second position. You have a hydroxy group. 1, 3 is going to be meta, and para will be 1, 4. And this 1, 2 is called as catechol. This is resorcinol, and this is hydroquinone, quinone or quinol. Next, let's start with ethers. Ethers, the general common name, you have the basic alkyl groups which are attached. So CH3OCH3, the 2-methyl groups. So that is dimethyl ether. That's it. So the common names are just going to be arrangement of the alkyl groups in the alphabetical order. So methyl N-propyl, M comes before P. So methyl N-propyl ether is CH3O. C2H, sorry, C3, CH3O, CH2, CH2, and CH3. Next is the IUPAC name. Now, IUPAC name of ethers. First of all, you'll have two parts. Okay, the alkyl group, which is smaller in length, will come up as an alkoxy group, whereas the one which is longer will be considered the parent. So let's take the example of this one. Okay, methyl and propyl ether, methane and propane. This is a methyl group, this is a propyl group. A methyl group is obviously shorter and smaller than the propyl group. So the methyl group will become methoxy. Okay, it's going to become alkoxy, and this 3-membered chain is going to become the parent. So that'll be methoxy, 1-methoxy propane. Next, you have methoxybenzene. Benzene becomes the parent because it has 6 carbon atoms. Methoxy just has 1. There's one more very interesting one over here. Yeah. So here you have a C6H5, okay, which is directly attached to the oxygen. Okay. And here you have a CH2 taken 6 times, 3. CH3. So basically this side you have 7 carbon atoms. Here you have just 6. So this 7 carbon atoms becomes the parent. So heptane. And 1 phenoxyheptane. So that's about it. So the 1 denotes the fact that it's the first carbon which is attached to. For the second, this is the second carbon in this chain. And 3 would be for the third carbon atom of the butane. Sorry. This, the third 3-methyl is to denote this carbon atom. So with that, we're done with ethers. In case of cyclic alcohols, you have a prefix cyclo, and the OH is considered to be attached to this first carbon atom. So cyclohexanol, 2-methyl cyclopentanol. So that we're done with the nomenclature of alcohols, phenols, and ethers. Let's quickly go over the structures of functional groups. So the OH in alcohol, the OH is attached to the carbon chain using a sigma bond. So there's only one single bond, so it's a sigma bond. And the bond formation will be because of an overlap between the sp3 orbital of carbon with an sp3 hybridized orbital of oxygen. That is the single bond form. Now, in case of alcohols, the bond angle is less than tetrahedral. This is because these two lone pairs of electrons and oxygen will repel each other. Because of that, these bonds will be pushed closer together, and due to that, the bond angle is less than that of tetrahedral. In case of phenols, on the other hand, the bond angle is the bond length is 136 picometer, and this is less than that of methanol. You notice it's 142 in methanol. In case of phenol, it's 136. This is because of a major reason. So these electrons on the OH will tend to undergo resonance, and this leads to a partial double bond character between the oxygen and the carbon bond. So this bond has a partial double bond character, and because of that, the bond length is slightly lesser than that of phenol. Next, in case of ethers, you have the bond pair, two bond pairs, and two lone pairs, and these are all arranged in a tetrahedral arrangement. Now, there'll be a repulsion between the alkyl groups. There will also be a repulsion between the lone pair of electrons on the oxygen atom. Due to that, the bond angle is greater than the tetrahedral angle. So the bond length is almost similar to that of alcohols. Let's learn about the preparation of alcohols. First of all, for any such thing, just write down the headings at least and keep them aside so that whenever you go through them, instead of having to go through all the reactions, just go through the headings and try writing the reaction on your own. So first is from alkenes. So alkene reacts with water in the presence of acid to give an alcohol. This is an addition reaction, and it follows the Markovnikov's rule. Negative part of the addendum gets attached to the carbon atom having less number of hydrogens. So in this case, CH and CH2, CH obviously has less number of hydrogen atoms. So the hydroxy group gets attached to this carbon. The mechanism will be uploaded in the next video. Next is hydroboration. So diborane basically is going to undergo reaction with alkene. Now what is happening is, here first this hydrogen is going to get attached to this carbon, and the BH2 is going to get attached to the last carbon atom. And this further reacts with two molecules of the alkene to give us a trialkyl borane. So this trialkyl borane is undergoing a reaction or is oxidized in the presence of hydrogen peroxide and sodium hydroxide. And this gives us an alcohol. Remember, this particular reaction looks like it has undergone it has anti-Markovnikov's addition, because in generally you have, if it followed the Markovnikov's rule, you should have had the OH group attached to this carbon atom, but it's actually attached to the last carbon atom, and it looks like it has undergone anti-Markovnikov's rule. Next, the alcohol which is obtained is going to be of an excellent yield as well. So from alkene, you have an acid catalyzed hydration and hydroboration. Next, from carbonyl compounds. So first you have a reduction of aldehydes and ketones. So aldehydes and ketones undergo reduction to give us alcohol. And this is done by addition of hydrogen, and this is in presence of a catalyst. So this is also called as catalytic hydrogenation. The catalyst can be a finely divided platinum, palladium, or nickel as well. Or we can use reducing agents such as sodium borohydride and lithium aluminium hydride. Lithium aluminium hydride is a very good reducing agent. So generally remember, aldehydes will give us a primary alcohol, whereas ketones give us a secondary alcohol. Next, reduction of carboxylic acids and esters. So carboxylic acids, they undergo reduction in the presence of lithium aluminium hydride, which is a very good reducing agent. And this in turn gives us a primary alcohol. But the issue with using lithium aluminium hydride is the fact that it's extremely costly. So what they do instead is they convert the acid to an ester by an esterification reaction. And further, this is going to undergo catalytic hydrogenation, like in this case, to give us an alcohol. And the other R dash will also form an alcohol as well. So that is about carbonyl compounds. Carbonyl compounds are undergoing reductions. Aldehydes are giving primary alcohols, ketones are giving secondary alcohols, acids are giving us an alcohol, primary alcohol, whereas esters will give us a mixture of two different alcohols. Next is from Grignard's reagent. So Grignard's reagent is RMGX. I'm sure you've learned about it even in haloalkenes and haloarenes. So what happens here is this R group has a partial negative charge and the magnesium atom will have a partial positive charge. And between carbon and oxygen in a carbonyl compound, you have oxygen is more electronegative than carbon. So carbon has a partial positive and oxygen a partial negative. So the negative part of the Grignard reagent, that is R, is going to come attack this carbon atom. And this bond is shifting this towards the oxygen that gives us the adduct. Now the adduct is going to undergo hydrolysis to give us an alcohol, and MgOH. So here you have methanol. Methanol is forming a primary alcohol, whereas aldehyde generally gives us a secondary alcohol. Okay, and whereas ketones give us a tertiary alcohol. Do not confuse this with the reduction reactions. These reactions are with the Grignard reagent, using the Grignard reagent. Using that, you get a primary alcohol for methanol and aldehyde, and ketone gives secondary and tertiary alcohols respectively. So preparation, first from alkenes, you have alkene undergoing a reaction with water in the presence of acid to give an alcohol. Diborane is reacting with alkene to form something called as a trialkyl borane. And this is further undergoing oxidation in the presence of hydrogen peroxide and sodium hydroxide to give us 3 molecules of the alcohol. Carbonyl compounds are undergoing reduction, and reduction can either be in the presence of addition of hydrogen in the presence of catalyst, or it can be using reducing agents like sodium borohydride and lithium aluminium hydride. Reduction of carboxylic acids is done through lithium aluminium hydride, whereas esters are used, and that is by catalytic hydrogenation. Grignard's reagent, you have a carbonyl compound, that is the aldehyde or ketone, are reacting with Grignard's reagent to give an adduct, which on hydrolysis gives us an alcohol. Methanol is giving us primary alcohol, aldehydes will give a secondary alcohol, and ketones a tertiary alcohol. As I told you, for preparation of alcohols, here also we have the various reactions headings first. So phenols are prepared, or rather it was first isolated from coal tar in the 19th century and was also called as carbolic acid. Now, the lab preparations are generally from various benzene derivatives. So you have it from haloarenes, from benzene sulfonic acid, from diazonium salts, and from cumene. So from haloarenes, you have 2 steps. All of these I've written it in the form of 2 steps. So it's easier for you instead of just by hearting the reaction. If you understand this as well, it will help you write the reactions on your own. So step 1. From haloarenes, so you have chlorobenzene here. It's reacting with sodium hydroxide, and temperature is at 623 Kelvin, and pressure is at 320 atmosphere. And this is leading to the formation of something called as sodium phenoxide ion. Now, this sodium phenoxide is undergoing acidification, so that's why you have an HCl over here for us to get a phenol. Next is from benzene sulfonic acid. So benzene is reacting with oleum. For you to remember what oleum is, recall what you learned in P block elements. So this leads to the addition of, or rather substitution reaction into by replacing the hydrogen with an SO3H. And this gives us benzene sulfonic acid. And this benzene sulfonic acid is heated with molten sodium hydroxide. Okay, and that is giving us a sodium phenoxide ion. That's why you have 1 and 2. 1 and 2 means that first this reaction took place, and then followed, after this particular reaction, the second step is this. Now notice NaOH and H+. So NaOH led to the formation of sodium phenoxide ion, similar to what we have in haloarenes. And this is undergoing reaction with H+, which means it's in the acidic medium to give us phenol. So basically you can just draw this over here. So the next one is from diazonium salts. Diazonium salts are basically the ones which have the N2 plus Cl minus. So first of all, aniline is getting converted to benzene diazonium chloride by the reaction with NaNO2 plus HCl. This is also called as nitrous acid. And the temperature is going to be 273 to 278 Kelvin. Further, this benzene diazonium chloride is going to undergo hydrolysis with water on warming, and this gives us this gives us phenol with nitrogen and HCl. The last one is from cumene. Cumene is basically an isopropyl benzene. Okay, so you have the benzene which is attached to an isopropyl group. So this is undergoing oxidation in the presence of air to give us cumene hydroperoxide. So COOH is getting, basically here the hydrogen is replaced with OOH. Now, this is not COOH, carboxylic acid. No, if you notice carboxylic acid, the C and carbon and oxygen have a double bond, and the carbon is actually bound to both the oxygen atoms. This is hydroperoxide, and this is undergoing a reaction or is treated with dilute acid, and this leads to the formation of phenol and acetone. So we're having cumene. It is undergoing oxidation in the presence of air to give us cumene hydroperoxide. And this is further reacting with dilute acid to give us phenol and acetone. Actually, acetone, which is a byproduct, is obtained in large quantities using this method. So from haloarenes, first step, you have chlorobenzene. It's reacting with sodium hydroxide to give us sodium phenoxide, which on treatment with acid gives us phenol. Here, benzene is reacting with oleum to give us benzene sulfonic acid. And this is undergoing the same reactions in this case, basically this part. Excluding this, remaining all the same. Temperature obviously is going to be different, but basically it's giving us a sodium phenoxide ion, which on reaction or which on acidification is giving us phenol. Aniline is reacting with nitrous acid to give us benzene diazonium chloride, which on warming with water or when it's treated with dilute acid gives us phenol. The last is cumene, that is isopropyl benzene, is oxidized in the presence of air to give us cumene hydroperoxide. And this further on treatment with dilute acid gives us phenol as well as acetone. With that, we're done with the preparation of phenols. Let's learn about the structures, or rather the physical properties of alcohols and phenols. Now, alcohols and phenols consist of an alkyl or an aryl group. If you're talking about alcohols, it's an alkyl, and phenols have an aryl group and a hydroxyl group. So the properties of alcohols and phenols is due to the presence of the OH group. And the nature of the alkyl and the aryl group will actually change the properties of alcohols. So before we start about, talking about boiling points and the solubility, let's just recap on this concept, hydrogen bonding. Hydrogen bonding is a bond, or rather an attraction between a more electronegative atom and hydrogen. And in this case, it's the oxygen atom. So there is going to be a hydrogen bond between the oxygen and the hydrogen atom. And since it's between two different molecules, this is actually an intermolecular hydrogen bond. If it's within the same molecule, it's an intramolecular hydrogen bond. Because it is between two different atoms, it's an intermolecular hydrogen bond. First of all, the boiling point. Boiling point of these alcohols and phenols, they increase with increase in the alkyl, the number of carbon atoms in the alkyl chain. And this because when there is an increase, there is also an increase in the van der Waals forces. So that in turn increases the boiling point. Now, if the branching of the carbon atom chain increases, there will be a decrease in the boiling point. And this is because, again, because of van der Waals forces. So because the van der Waals forces will decrease due to the decrease in the surface area. Now, as I told you, OH groups in alcohols and phenols, they form intermolecular hydrogen bonds. And because of that, alcohols and phenols have higher boiling points compared to, haloalkanes, hydrocarbons, and ethers, or even haloarenes of a comparable atomic mass, or rather, comparable molecular mass. So here you have ethanol and propane and methoxymethane. So this is an alcohol, this is an ether, and this is an alkane. And notice here you have the molecular mass, which is 46 and 44 in case of propane, and the boiling points. Now, ethanol has the highest boiling point compared to the other two. and propane is the least, but methoxymethane is in between propane and ethanol. And the reason why you have a high boiling point is again because of hydrogen, intermolecular hydrogen bonding. Whereas our ethers and alkanes do not have intermolecular hydrogen bonds. Next is solubility. It's again to do with the fact that they can form hydrogen bonds. Now, because they are able to form the hydrogen bonds, they are alcohols are actually soluble in water. But when there is an increase in this alkyl group, okay, there will be a decrease in solubility. So if there is more, if the chain is longer, that will in turn lead to its effect on the solubility of an alcohol. Now, lower molecular alcohols are actually miscible in water in all proportions. So for understanding the physical properties, you need to remember hydrogen bonds. First of all, if there is any increase in the alkyl group, there is an increase in the boiling point. Second, if there is a branching in the alkyl group, there is a decrease in the boiling point. Both of this is because of van der Waals forces. Next, alcohols and phenols have the highest boiling point compared to haloalkanes, haloarenes, hydrocarbons, and even ethers of a comparable molecular mass. And the reason alcohols have a higher boiling point is because of the fact that they are able to form hydrogen bonds. The reason they are soluble in water is also because of hydrogen bonds only. And if there is an increase in the alkyl chain, there will be a decrease in the solubility of the alcohol. With that, we're done with the physical properties of alcohols and phenols. Alcohols are extremely unique. This is because they can act as both nucleophiles as well as electrophiles. Now we are going to be discussing about the chemical properties of alcohols and phenols. So when they act as nucleophiles, what happens is the bond between the oxygen atom and the hydrogen atom is broken. And when they act as electrophiles, the bond between carbon and oxygen is broken. So here, when they act as nucleophiles, that is nucleus loving, which means they have a negative, they have more electron density. So here, the lone pair of electrons on the oxygen atom will attack this carbon. And what happens is the oxygen atom gets a positive charge. And since it cannot be, it cannot have a positive charge, the hydrogen gets lost. And that's done as a H plus ion. Whereas when they act as electrophiles, here there is another H plus. So basically, the protonated alcohols will react in this manner. So here you have H plus getting added, and this leads to the formation of OH2. So the bromine, which is a nucleophile, is going to come attack the carbon, the CH2, and this leads to the breakage of the CO bond. And this leads to the formation of a new compound. So based on the cleavage of OH and CO bonds, the reactions of alcohols are classified into two. First is obviously involving a OH bond. So there we'll be studying about acidity and esterification. Second is the reactions involving the cleavage of CO bonds in alcohols. And this includes the reaction with hydrogen halides, reaction with phosphorus trihalides, dehydration, and oxidation. Last, we'll be learning about the reaction of phenols. And as always, I've written down all of these as a separate section so that you can go through it and recall it as in when you read these. So let's start with the reactions involving cleavage of OH bonds. So acidity of phenols, or rather, I think it's supposed to be acidity of alcohols and phenols. So when you have reaction with metals like sodium, potassium, or aluminium, alcohols are forming alkoxide and hydrogen, whereas a phenol is forming a phenoxide and hydrogen. So this shows that alcohols and phenols are acidic in nature. Here you have a tertiary butyl alcohol. It's reacting with aluminium to form the aluminium tertiary butoxide as well as hydrogen. Phenols not only react with sodium, but they also react with sodium hydroxide to form sodium phenoxide. If you remember, when we studied about the preparation, sodium phenoxide was one of the compounds in the intermediate steps in the synthesis of phenol. So sodium phenoxide converted to phenol on reaction in the presence of HCl. So phenol on reaction with sodium hydroxide is giving us sodium phenoxide as well as water. So all these reactions show that alcohols and phenols are acidic. Now they basically donate the H plus ion to a Bronsted base, and that is why they are called as acids. Okay, now acidity of alcohols. First of all, obviously the OH bond is polar in nature. So what happens is the oxygen atom is going to have a negative charge, right? Or is going to have a partial negative charge, whereas a hydrogen is going to have a partial positive charge. So this means that the OH bond is actually polar in nature. Now, when we compare primary, secondary, and tertiary, the acidity in case of primary will be higher. And this is because when you have a primary, so R groups are basically electron releasing in nature. Right. So when you have just one R group, the amount of electron releasing capacity to the CH2OH is comparatively less than in case of tertiary. Tertiary, you have three alkyl groups which are releasing the electrons. So basically what happens is when the hydrogen atom is lost, the O minus which is formed will be unstable because of a lot of electrons in this case, and also the O minus charge. So because of that, the primary alcohol is more acidic than secondary, which is more acidic than tertiary. Now they're obviously weaker acids than water. So when water is reacting with an alkoxide, it's leading to the formation of ROH as a conjugate acid and OH minus as a conjugate base. So this shows that water is actually a better proton donor, which makes it a stronger acid compared to the alcohol. And the alkoxide is actually a good proton acceptor, which makes it a good base. Now, the next one is acidity of phenols. So we know that when phenol reacts with metals, it leads to the formation of the phenoxide. And that's what we learned over here. And can also react with sodium hydroxide to form sodium phenoxide and water. Now, the reason you have the stability coming in for phenols and the ability for them to, basically, even if they lose the hydrogen atom, they're quite stable. It's because of the resonance stabilization. And remember, resonance stabilization shows that the negative charge is is present at the ortho and the para position because OH is an electron donor, and this is very, basically it's an electron releasing group. I'm sorry, I shouldn't have used the word electron donor. It's an electron releasing group, and because of that, the ortho and the para position become electron rich. So the sp2 is more electronegative. So what happens is more electronegative than the OH which is attached. So the electron density on the OH will decrease, and this will make sure the OH, the bond between OH, is becoming more polar in nature. And this in turn will increase the ionization of phenols, but this particular property is not observed in alcohol. So in alcohols, it's just the ROH, RO minus. But in case of phenols, you have the whole concept of the sp2 hybridized carbon atom being more electronegative than compared to the OH group. Now, the reason you have the stability the reason we're studying about stability is because you need to know that, okay, even if the RO minus is formed, is it stable for it to donate the hydrogen atom in the first place? So the negative charge in the RO minus is actually localized, which means it's going to stay on the oxygen atom. Whereas in case of phenoxide ion, the negative charge is going to undergo delocalization. And because it is delocalized, it is more stable. So the alkoxide ion is less stable than the phenoxide. So here you have the various resonance structures. I'm assuming you have, you remember learning about resonance in grade 11, and that's just here. So here also the O minus is going to act as an electron releasing group. Now we've learned about we've learned about the stability, the acidity of phenol and phenoxide ion. Obviously, phenols can also be substituted. So when you have the electron withdrawing group in ortho and para position, what happens is the acidity of phenol increases. Now, basically, here, if you notice, the phenol, or rather, let's take these structures. Okay, now assuming you have an electron withdrawing group at this position and this position, the negative charge, which is getting delocalized, is going to get more stable. And because of that, the ortho and para position is more stable. But if you have, the phenol group having an electron withdrawing group at the ortho and para position is more acidic than the electron releasing group containing phenol. Now, what happens is already here at the ortho and para position, you have a negative charge, which means they're electron rich in nature. So if you have an electron releasing group in these two positions, obviously the ability of the hydrogen atom to be removed from the phenol and the stability of the O minus itself in case of phenoxide is going to be reduced. And because of that, when there is an electron releasing group, there is a decrease in acidic strength. And in the presence of electron withdrawing group, there is an increase in acidic strength. And this is at ortho and para positions. So here you have pKa values. So higher is the pKa value, lesser is the acidity. So basically it means lower is the pKa value, more will be the acidity. Notice over here you have ortho nitrophenol and ortho. First of all, nitro group is an electron withdrawing group, and it's at the ortho position, its acidity is quite high. And even para position also, there is a high amount of acidity. So ethanol, on the other hand, is less acidic than phenol, and that's obvious from the fact that its pKa value is 15.9. Next, let's study about the esterification reaction. So alcohols or phenols, when they react with carboxylic acid, they lead to the formation of ester. Now, this can be in the presence of carboxylic acid, acid anhydrides, or acid chlorides. So the second is the acid anhydride, and the third reaction is an acid chloride. So when you have, so this is an ester, RCOOR dash. So when they react with carboxylic acid and anhydride, water which is formed is constantly removed. This is because if you notice here, you have a double arrow, which means a forward reaction is possible, a backward reaction is also possible. So if the water quantity starts to increase, it will lead to the reversal of this reaction for us to get back the initial reactants, and we don't want that, right? So what they do is they remove the water molecules as and when it's formed. Next, for acid chlorides, the pyridine is used, and this is because it neutralizes the HCl which is formed. So again, similar to water, if pyridine was not added, if the HCl stayed the same, then it would have gone back, and that in turn would have given us the alcohol and the acid chloride, and we don't want that again. So pyridine is basically used for neutralization of the HCl which is formed. The last one is acetylation. So acetylation, basically, as the name suggests, is the introduction of the acetyl group in alcohols and phenols. Here we have salicylic acid. So salicylic acid is undergoing acetylation with acid anhydride to give us acetyl salicylic acid, which is aspirin. And this is the byproduct, which is acetic acid. With that, we're done with the reactions that involve the OH group. Next, let's look at the reactions that involve the cleavage of the CO bonds. So first is the reaction with hydrogen halides. So ROH, which is an alcohol, is reacting with a hydrogen halide to give us an alkyl halide plus water. Pretty simple, right? So this is very important. It's called Lucas test. So Lucas test consists of something called as a Lucas reagent. That is concentrated HCl and ZnCl2. So basically, this is the reaction that's going to take place. But the thing is, Rx, which is formed, is insoluble in the Lucas reagent. So the ROH will be soluble in the Lucas reagent, but the Rx will be insoluble. And because of that, it will give us a precipitate. So tertiary alcohols, what happens is the precipitate or the turbidity is almost formed instantaneously. In secondary, it takes like 2 to 3 minutes, or 3 to 5 minutes rather. And in case of primary alcohols, you observe turbidity only when the mixture is heated. And this is how we differentiate between a primary alcohol, a secondary, and a tertiary alcohol. Next is the reaction with phosphorus trihalide. Now, this reaction is something you learned in haloalkanes and haloarenes. So alcohol is reacting with phosphorus trihalide to give us alkyl halide. And here you have 3 molecules because it's a PX3 to make sure the reaction is balanced. You're getting 3 molecules of an alkyl halide and H3PO3. The alkyl halides can be PCl3 or PBr3. Sorry. The phosphorus trihalides can be PCl3 or PBr3. Next is dehydration. So this is basically the opposite of the first method of preparation of alcohols. There we reacted alkene with water in the presence of catalyst to give us an alcohol. Here it's just the opposite. You have alcohols reacting with a protic acid or catalyst to give us alkene. So the protic acid can be a concentrated H2SO4, H3PO4, and the catalyst is anhydrous ZnCl2 or alumina. So here you have C. This is an alcohol. So you're heating it in the presence of acid. So what happens is HOH is getting lost as water, and the alkene is formed. It's just the opposite of the preparation reaction. So ethanol is reacting with concentrated H2SO4 on heating to give us ethene. And this is at 443 Kelvin. Now, secondary and tertiary alcohols, they are reacted under milder conditions because they're easily getting converted to the respective alkenes. And this is, so here you have propanol is giving propene, and you have tertiary alcohol. If you notice, the alcohol, in case of tertiary alcohol, the conditions are much more milder compared to primary and secondary alcohols. And this is easier to dehydrate. So the order of dehydration is tertiary is more, I mean, it's easier to dehydrate tertiary compared to secondary compared to primary. In the next video, I will be uploading the mechanisms explanation. Next, oxidation, that is dehydrogenation. Now, when we were studying about the synthesis of alcohol, we learned that aldehydes and ketones are undergoing reduction to give us an alcohol. And we also studied about carboxylic acids undergoing reduction to form alcohol. So alcohol undergoes oxidation to give an aldehyde, followed by after that it will form a carboxylic acid. And this is formed by because the H and C bond is going to break, and the O and H bond is also going to break to give us a double bond between the carbon and the oxygen atom. So the loss of dihydrogen is going to take place to give us an aldehyde, followed by after which we get a carboxylic acid. So when we use strong oxidizing agents, we have a direct conversion of alcohol to a carboxylic acid. But when we use CrO3 in anhydrous medium, that will give us the aldehyde. So basically, this is the this is the reaction, complete reaction. And when we want the acid directly, we are using an strong oxidizing agent like acidified KMnO4. When we want it at the aldehydic stage, we are using CrO3 in anhydrous medium. Now, in case of conversion from primary alcohol to aldehyde, the oxidizing agent used is pyridinium chlorochromate. And what happens is we are going to get the respective CHO. Now notice one thing over here, the double bond over here is not getting changed. It stays the same, but it's only the CH2OH which has gotten converted to an aldehyde. Next, in case of secondary alcohols, we will get ketones. So primary alcohols are giving aldehydes, secondary alcohols gives ketones. Remember, aldehydes on reduction give primary alcohols, ketones on reduction give secondary alcohols. It's just the opposite of what we learned over there. So when we use chromium anhydride as the oxidizing agent, we get a ketone. Tertiary alcohols actually do not undergo a reaction, or they don't undergo oxidation. So they require extreme conditions like a very strong oxidizing agent as well as the elevated temperature to undergo oxidation. So when tertiary alcohols do undergo oxidation, they give us a mixture of carboxylic acid. And these carboxylic acid will actually contain less number of carbon atoms than you expected to. Next is reaction with copper. Now, when we have the alcohol, we pass the vapors over heated copper at 573 Kelvin. What happens is the primary and secondary alcohol will undergo dehydrogenation. So they are giving us aldehydes and ketones. But tertiary alcohols are undergoing dehydration. So they give us an alkene. So again, to recall, primary and secondary alcohol is undergoing dehydrogenation to give us aldehydes and ketones respectively. Whereas tertiary alcohols is undergoing dehydrogenation for primary and secondary alcohols. In case of tertiary, it's undergoing dehydration reaction. So with that, we're done with the 4 different reactions. Remember, 2 of these are just opposite of one of, the preparation that you learned. And this is basically whatever you learned in haloalkanes and haloarenes. And I think reaction with hydrogen halides is also something you learned in haloalkanes and haloarenes. Something new is the Lucas reagent or Lucas test also. The last one is reactions of phenols. Now, as you remember, phenols can undergo electrophilic aromatic substitution reactions. Now, the reason that's the case because you have and that will be at the ortho and the para position. This is because an electrophile is electron loving, and due to the resonance, that is OH is an electron releasing group, so the ortho and the para position become electron rich. So because of that, we'll observe products present at the ortho and the para position. So let's look at reactions. First, phenol reacts with dilute HNO3 to give us orthonitrophenol and paranitrophenol. Now, what happens is, in case of orthonitrophenol, it has intramolecular hydrogen bonding. Okay, because of the oxygen of the nitro group and the hydrogen of the OH group. Whereas paranitrophenol has intermolecular hydrogen bonding between 2 different compounds. 2 different molecules of the same compound. So what happens is, they can be separated easily using steam distillation. And this is because intramolecular hydrogen bonding containing orthonitrophenol is steam volatile, whereas intermolecular hydrogen bonding containing paranitrophenol is it's less volatile compared to orthonitrophenol. So we can separate these two using steam distillation. Now, when we change the conditions, we get a different product. Phenol is reacting with concentrated HNO3 to give us picric acid, which is 2,4,6-trinitrophenol. But the issue with this particular reaction is that the picric acid which is formed, the yield is not that great. And when the yield is not that great, it's not it's not worth basically using so many reagents and getting those products. Instead, picric acid is done by this method. So phenol is reacting with concentrated H2SO4 to give us phenol 2,4-sulfonic acid. First, we're getting phenol 2,4-sulfonic acid. This is reacting with the concentrated HNO3 to give us 2,4,6-trinitrophenol. So basically H2SO4, phenol and H2SO4 is giving us phenol 2,4-sulfonic acid, which on reaction with concentrated nitric acid is giving us picric acid. Next is halogenation. So halogenation, usually based on the conditions, you get the variation in products. So first of all, you have first condition is low polarity solvent like CH3L3 or CS2 and a low temperature. And the product which is formed is monobromophenols, which means bromine is present in only one of the positions, that is ortho or para. And obviously, ortho position is going to be minor because of steric factor. Now, notice over here, when we use benzene and it underwent halogenation, it is in the presence of Lewis acid like Fe3Br. But because of the presence of the hydroxy group of the phenol, it actually is quite reactive towards bromine and it does not require any extra Lewis acid like Fe3Br. Now, in case of phenol, when it reacts with bromine water, it gives us 2,4,6-tribromophenol. So all the 3 positions, that is both the ortho positions as well as the para positions, are getting substituted with bromine. And the only thing between the difference between this and this is the fact that here it is bromine in CS2 at 273 Kelvin, that is in the presence of a low polarity solvent. Here we are directly reacting it with bromine water. Next is the coal-base reaction. Coal-base reaction, phenol reacts with sodium hydroxide to give us the phenoxide ion. And this phenoxide is actually more reactive to electrophilic aromatic substitution. So what happens is it reacts with a weak electrophile like carbon dioxide as well. And this gives us an orthohydrobenzoic acid, that is salicylic acid. So here, if you notice, sodium phenoxide is more reactive, and because of that, it is able to react with a weak electrophile to lead to formation of salicylic acid. Next is the Riemann-Tiemann reaction. Phenol is reacting with chloroform in the presence of sodium hydroxide to give us the substituted benzyl chloride. This is undergoing further reaction with sodium in the presence of sodium hydroxide. So this CHCl2 is getting changed to CHO. After which, it's under this ONA is obviously going to get converted back to OH in the presence of an acid. So here, remember, we have the CHO group getting introduced at the ortho position, and that's called as salicylaldehyde. When it's COOH, it is salicylic acid. When it's CHO, it is salicylaldehyde. So you have chloroform and aqueous NaOH to give us the intermediate. So you have CHCl2 just getting added over here. And after that, you have the in the presence of NaOH, it's leading to the formation of CHO, that's an aldehyde. And the ONA has to get converted back to OH to give us salicylaldehyde. And this is done in the presence of an acid. The next one, the fourth reaction, phenol is reacting with zinc dust. When phenol reacts with zinc dust, it gives us benzene plus zinc oxide. Oxidation of phenol, it undergoes oxidation in the presence of chromic acid to give us benzoquinone, which is a conjugated diketone. So basically, it's undergoing oxidation to give us two double bonded O on the para position compared to OH, and the double bonds are basically shifted to make sure that the carbon atoms have just 4 bonds each. So in presence of air, the phenols actually undergo oxidation to give dark colored mixtures containing quinones. So with that, we're done with the reactions of alcohols. First, we started with reactions with respect to the acidity of alcohols and phenols. The reason they are acidic is because of their ability to form alkoxides and phenoxides. Alcohols are less acidic than water because in the presence of, where is the reaction? Right. So here this is the alkoxide ion. When it reacted with acid, it actually acted as it formed ROH and OH minus. And next, acidity of phenols. Phenols are acidic, and the phenoxide ion, which is formed, is more acidic. More stable due to resonance compared to the alkoxide ion. Presence of electron withdrawing groups at the ortho and the para positions increases the acidity of phenols, whereas electron releasing groups at ortho and para positions decrease the acidity. Esterification reaction, the alcohols undergo esterification with carboxylic acid, acid anhydrides, and acid chlorides to give us esters. Next is the various reactions to do with the breakage of carbon-oxygen bond. First one was basically alcohols reacting with hydrogen halides to give us alkyl halides and water. The Lucas test is used for the understanding, or rather for us to understand, to differentiate between primary, secondary, and tertiary alcohols. Reaction with phosphorus trihalides is something that you learned in aldehydes, alcohols. Haloalkanes and haloarenes. So alcohols react with phosphorus trihalides to give us the alkyl halide. Dehydration is the opposite of synthesis of alcohol from alkene. In that case, we had alkene undergoing reaction with water in the presence of catalyst to give us an alcohol. The opposite of that is the synthesis of alkene from an alcohol. And the mechanism, I'll put it up as a separate video. Here you have the primary requires stronger conditions compared to secondary and tertiary. So the order of dehydration is tertiary undergoes more dehydration relatively more easily than secondary than compared to primary. Next, you have the oxidation of dehydrogenation. So this is again the opposite of synthesis from carbonyl compounds. Carbonyl compounds undergo introduction to give us alcohols. Alcohols undergo oxidation to give us carbonyl compounds. So primary alcohol gives us aldehyde, secondary alcohol will give us the ketone. And reaction with copper also, this is also actually can be, this can also show the difference between primary, secondary, and a tertiary alcohol. So primary, secondary are giving aldehyde and ketone respectively, whereas tertiary is undergoing dehydration to give us an alkene. Last, we learned about the reaction of phenols. The electrophilic aromatic substitution groups are added at the ortho and the para position because OH is electron releasing in nature. With dilute HNO3, orthonitrophenol and paranitrophenol are formed, and they're separated using steam distillation. Whereas in concentrated HNO3, we are getting picric acid or 2,4,6-trinitrophenol. So because this reaction is not giving a good yield, We are reacting it with concentrated H2SO4 to give us phenol 2,4-sulfonic acid, which on concentrated HNO3 give us picric acid. Next is halogenation. Again, because of the variation in terms of conditions, we have variation in terms of the products formed. First of all, benzene reacts in the presence of Lewis acid, but phenol does not require a Lewis acid because it itself is quite reactive because of the electron releasing nature of phenol, of the OH group. So in case of the low polarity solvent like CHCl3 and low temperature, we are getting monobromophenols, and bromo in case of ortho position is considered a minor product because of steric hindrance. Next, in presence of bromine water, we are getting 2,4,6-tribromophenol. Next, coal-based reaction. This is a named reaction. Phenols reacting with sodium hydroxide to give us phenoxide ion. Phenoxide ion is more reactive to electrophilic substitution, and so it reacts with a weak electrophile like carbon dioxide to give us salicylic acid. So orthobenzoic hydrobenzoic acid is the main reaction product formed. Next is remertemin. Remertemin is we are getting salicylaldehyde. Remember, coal base we're getting salicylic acid, and remertemin we're getting salicylaldehyde. So here you have it reacts. Phenol is reacting with chloroform in the presence of sodium hydroxide to give us a substituted benzyl chloride, which is the intermediate. On hydrolysis will give us salicylaldehyde. Next, reaction of phenols with zinc dust. So phenol is undergoing a reaction with zinc dust to give us benzene. So OH group gets kicked out. Next, oxidation. Phenol reacts with chromic acid to give us benzoquinone, which is basically undergoing oxidation reaction over here because the double bond O gets added and the hydrogen is getting kicked out. So you have actually, yeah, so that's pretty much it. So in the presence of air, phenols actually undergo slow oxidation to give us dark colored compounds. If you find reactions difficult, as I did at one point in when I was in grade 12, I found reactions very difficult to remember. And so the whole writing it as a list of reactants and products helped me way better than trying to memorize it as such could. So that we're done with the chemical properties of alcohols and phenols. Uses of commercially important alcohols, methanol and ethanol. So methanol is CH3OH, ethanol is C2H5OH. So it is, so let's go and start on with methanol. It's also called wood spirit because it was produced by destructive distillation of wood. So carbon monoxide is reacting with hydrogen in the presence of zinc oxide and Cr2O3 as a catalyst at the temperature of 573 to 673 Kelvin and pressure of 200 to 300 atmosphere to give us methanol. So it's a colorless liquid and it boils at 337 Kelvin and it's very poisonous in nature. So small quantities can actually cause blindness and large quantities can also cause death. So the uses of methanol include in paints and varnishes, and it's used also for making formaldehyde. Generally in the labs and all, the alcohol, the ethanol which is present is actually it's not pure ethanol, but it has some amount of methanol added to it. This is to make sure that people don't accidentally drink it. Or, yeah. So the next is ethanol. Ethanol is produced by fermentation, and this is one of the oldest methods. So first, sugar and molasses, sugar canes or sugar canes or fruits are going to get converted to glucose and fructose using the enzyme invertase, and this is further undergoing reaction, fermentation, with in the presence of enzyme zymase to give us ethanol and carbon dioxide. So in wine making, what they do is they use grapes, okay, and when the grapes ripen, the quantity of the sugar increases inside grapes and the yeast starts to grow around the surface. So basically they just crush the grapes and the sugar comes in contact with yeast to give us ethanol, and this is done in the anaerobic conditions and carbon dioxide is released, and if the oxygen percentage increases or if it's in the presence of air, we actually get a mixture of ethanol and ethanoic acid, and this destroys the taste of alcohol. And one more thing, the percentage of alcohol, if it exceeds 14%, the enzyme zymase will inhibit and this will lead to the stop of the production of alcohol. That's ethanol. Next is it's a colorless liquid and the boiling point is 351 Kelvin. It's a solvent in paint industry and the preparation of various carbon compounds. The denaturation of alcohol. So it is made unfit for drinking, as I just told you, but they add copper sulfate and pyridine, which is a foul-smelling liquid. Large quantities of ethanol are obtained by hydration of ethene. With that, we're done with ethanol and methanol, which are commercially important alcohols. So ethers. Ethers are compounds which have an alkyl, an oxygen, and another alkyl group. Basically, an alcohol where the hydrogen is replaced with an alkyl group is an ether. So first method of preparation is dehydration of alcohols. So as we know, alcohols undergo dehydration with a protic acid at a high temperature to give us an alkene. So when the temperature is reduced, it gives us an ether. So this reaction condition actually is very important, and based on the reaction condition we get, that is the temperature, we get the various products. So the mechanism, it will be discussed in the next video. So there are two very important points. There is some amount of alkene which will form in the present, in this reaction along with the ether. The reason is when there is an increase in temperature, so to avoid the whole formation of alkene, the temperature has to be controlled. And if there is an increase in temperature, then the alkene is formed. Temperature has to be controlled it has to be controlled to the maximum extent possible. Next is alkyl groups should be unhindered. Now, if you remember, when we studied about the properties of alcohols, the primary alcohols undergo dehydration to a less extent compared to a tertiary alcohol. So the conditions required for tertiary alcohols to undergo dehydration is milder compared to primary, and then secondary, and then primary. So that's the order. So tertiary undergoes dehydration easily compared to secondary, which undergoes dehydration easily compared to primary. So because of that, this method can be used for the synthesis of the ether, which has only a primary alkyl group attached to it. Secondary and tertiary alcohols will give alkenes as the product under the same reaction conditions, because they require milder conditions for it to undergo dehydration reaction. Next is Williamson synthesis. Williamson synthesis, basically you have Rx plus, that's an alkyl halide, is reacting with sodium alkoxide to give us an ether with the sodium halide. So here in this case, you have the secondary and the tertiary alkyl groups containing ethers can also be prepared using this method. But when we talking about the alkyl halide, if the alkyl halide actually has a tertiary alkyl group attached to it, then you have the alkene as the only product formed. The reason that this is the case, because elimination competes over substitution. The alkoxide not only acts as a strong base, it acts as a strong base, not just as a nucleophile. So it can react as a base as well. And they lead to the formation of an alkene, which is an elimination product. Next, phenols are getting converted to ether using this method. So you have sodium phenoxide ion reacting with alkyl halide to give us basically an ether. With that, we're done with the synthesis of ethers. Dehydration of alcohols at normal conditions, at certain conditions, that is a high temperature, we get an alkene, but at a lower temperature, we get an we get an ether. So two conditions: first, temperature has to be controlled to make sure that the alkene is not formed, and the primary alcohols can only be converted to an ether using this method, because secondary and tertiary can get converted to an alkene at lower temperatures as well. And this is because they undergo dehydration to an much more easily compared to a primary alcohol. Williamson synthesis, basically an alkyl halide is reacting with sodium alkoxide to give us ether plus sodium halide. So here in this case, you can have a tertiary alkyl group also for the ether, but remember, it's only the alkoxide which can have a secondary or tertiary. If it's the alkyl halide which has a secondary or tertiary, it leads to the formation of an elimination product. We are getting an alkene instead of an ether. And it acts as a strong base, not just as a nucleophile, and because of that, we're getting the alkene. Phenols are converted to ethers using the same method. With that, we're done with the preparation of ethers. Physical properties of ethers. Carbon-oxygen bond in ether is polar because the oxygen atom is more electronegative than carbon. And so the ethers actually have a net dipole moment. Now, net dipole. Boiling point of ethers. So the weak polarity does not actually affect its boiling point. So boiling point of the ether is actually quite close to that of the alkane of a comparable molecular mass. And one more thing, the boiling point of ether is actually quite lower compared to the that of the alcohol. And this is because alcohols have the tendency to form hydrogen bonds. Next, solubility. So they are miscible in water. This because the oxygen atom in ether is capable of forming a hydrogen bond with water. And this is quite similar to what we observe in alcohol. So ethane and butane one these have a comparable molecular mass, and they are miscible in water to a similar extent. So it's 7.5 and 9 grams per 100 ml of water. With that, we're done with the physical properties of ethers. Let's look at the chemical reactions involved in ethers. So first of all, ethers are the least reactive functional groups, and drastic conditions are required for them to undergo a chemical reaction. So here we have the cleavage of CO bonds in ethers. So what happens is the ether is reacting with HX, which is the hydrogen halide molecule, to lead to the formation of two alkyl halides. So here the RX and the ROH, then this ROH will again react with another molecule of HX to give us RX plus H2O. In case of aryl halides, the cleavage takes place at the OR bond, and this leads to the formation of phenol and an alkyl halide. When we have two different alkyl groups, we have the both of these are cleaved in the same manner. And the reactivity of hydrogen halides is HI is more reactive compared to HBr than HCl. So this is the mechanism, and this will be discussed in detail in the next video. Ethers also undergo, that is the anisole, which is basically benzene with an OCH3, that undergoes the electrophilic substitution reaction. And it is ortho-para directing because negative charge is present at the ortho and para group. And this means that the electrophile will come attack the ortho and the para positions. So first is halogenation. So anisole undergoes reaction with bromine and ethanoic acid to give us two products, para-bromoanisole and ortho-bromo. And obviously ortho will be the minor product because of steric factor, whereas in case of para, you don't have that issue. And so the para-bromoanisole will be the major product. And in this particular reaction, it takes place in the absence of iron 3 bromide as a catalyst because OCH3 is as such a ring activating group. Next is Friedel-Crafts reaction. Anisole undergoes this reaction, obviously, so it reacts with alkyl or acyl halide to give us an alkyl or acyl group at the ortho and the para position. So your ortho position will be the minor product, again due to steric factor, than the para position. Also, the catalyst used is anhydrous AlCl3. So here you have it reacting with CH3Cl, which is an alkyl halide, to give us an alkyl group at the ortho and para position. There is a 2-methoxytoluene, 4-methoxytoluene respectively. And in case of ethanol chloride, which is an acyl chloride, to give us 2-methoxyacetophenone and 4-methoxyacetophenone as the major product. Next is nitration. So anisole reacts with concentrated H2SO4 and HNO3 to give us a nitro group at the ortho and the para position. And obviously, as it is with all the other electrophilic substitution reactions, we have the minor product at the ortho position. With that, we're done with the chapter alcohols, phenols, and ethers. There's only 3 reactions, or one more. I'll just do it once more. So you have the cleavage of CO bonds and ethers. This leads to the formation of an alkyl halide. Basically, they require very drastic conditions when basically an alkyl aryl halide, sorry, here in case of the alkyl aryl ether, you have the cleavage of the CO OR bond taking place to give us a phenol and an alkyl halide. Next, you have the electrophilic substitution reactions. You're learning about halogenation, Friedel-Crafts reaction, and nitration. Halogenation takes place in bromine and ethanoic acid. We're getting para and ortho products, and the ortho is the minor, para is the major product. Friedel-Crafts reaction give us the alkyl and the acyl groups at the ortho and the para position. And again, here also the ortho position products are the minor products. Next, anisole is undergoing nitration in the presence of H2SO4 and HNO3 that is concentrated to give us ortho and para nitroanisole. So again, here as well, the ortho position product is a minor product. So with that, we're done with alcohols, phenols, ethers. Feel free to check out the notes which have been uploaded in the description below. I hope that helps. And if you have any suggestions, comments, questions, queries, anything, do comment below, or you can reach out to me on my email. With that, we're done with alcohols, phenols, ethers, but the reaction mechanisms of a few reactions we'll be discussing in the next video, so do check it out. Oh, and one more thing, the P block elements chapter has also been uploaded, and it's to do with whatever you have for the exams of the year 2021-2022. All the best.